going to be talking about, oh, there we go, some of the research I have been doing in the past year. So the way to pronounce that word is polyoxometallate. And these, if you break down the word, poly, multiple, oxo, oxygen containing, metallate, metal containing. These are kind of 3D structures that have got loads of different uses and purposes. And basically what I'm trying to do is explore their use to kind of help the net zero challenge. So just to kind of introduce that, as I know we're all aware, but in order to meet net zero for 2050, a massive part of this is going to be PV, so photovoltaic, solar power, energy. Probably not possible to do without it, but the issue with current PV methods is basically that you have these kind of really big, really heavy modules that are, they've got a lot cheaper in recent years, but they're still very expensive. They use a lot of non-earth abundant materials. So you can see on this periodic table here, anything with a colour is in varying levels of risk of running out in the future. And we use a lot of metals from this area of the table. I don't know if my laser pointer's on, so I can't tell if you can see what I'm pointing at. There we are. Okay. So around here, a lot of stuff comes from this region. And these modules here are silicon, which is like standard practice. We've all seen these everywhere. And generally, they use a lot of not environmentally benign materials, or they use a high temperature fabrication. So obviously, yeah, we want to make net zero goals, but if you're doing this with stuff that's actually damaging the environment, it almost seems counterproductive. So we're exploring the use of polyoxometallates. On the right here, you can see the different structures of these, and these are basically little tiny molecular structures, and they have all different kinds of structures. There's literally millions of them, but the ones I'm focusing on is a keggin, and basically they're just formed from group 5 or group 6 transition metals in the highest oxidation state, which means that they're D0, so they've got no electrons on them, and they're kind of an intermediate between mononuclear oxo or hydroxometallates and polymeric metal oxides. So they're not kind of the semiconductor structure of nickel oxide or titanium or anything like that. They're not, superstructures, but also they're not little tiny discrete particles either. They have quite a large extensive structure. And they're essentially formed of these, when I say polyhedra building blocks, it's kind of each of these little triangles you see. And basically these have a vast array of chemistry. They're really stable to redox chemistry, which means that they're stable to adding and removing electrons. And this is because their structure's really, really stable because of the metal oxide bonds. And you can kind of vary these loads with different metals and non-metals being incorporated, such as here, you've added in phosphorus. And again, this opens up another kind of wealth of chemistry. So they've got loads of doors to kind of open. And how do they form? So I'll try and go through this quickly as it is a bit chemistry heavy. So it's usually called serendipitous formation or self-assembly, which means you kind of chuck a load of things in a vessel, let them mix, and then out you get POMs, which sounds quite simple, but it's not, believe me. And typically we use large group 4D or 5D metals, which means they can actually coordinate to a lot of different other metals, which means you get these polymeric structures, right? So an example of a kind of single metal oxide would be this chromium oxide. And because it's only in the 3rd D group, it's actually really tiny and can't coordinate to many metals or oxygen atoms. So it just kind of stays as this tiny little structure, and it's a dimer, whereas here you've got this tungstate, which is an isopolyanion, so it's like an actual big 3D structure. And basically, what controls their formation is your experimental conditions. So you effectively have a load of different equilibria going on, loads of different complicated reactions in solution all taking place at the same time. And what you want to do is control what you put in to control what you get out. by acting on these different equilibria states. So even with the same kind of starting materials, if you vary, well, the type of anion and its concentration, things like pH, ion strength, all of these variables at the bottom here control what you get out. So they're really tunable, and actually, again, you have big access to a lot of different structures, even just from simple starting building blocks. So obviously, there's a lot to explore there. And why do they form? Again, this I'll go through quite quickly, but it's the kind of idea that each atom can only occupy one edge-shared polyhedron, so resulting in metal oxide bonding. So you can't, it's basically space and size restriction. You can't just get random metals forming with random oxygens and crossing with each other. They have to be in a very kind of ordered arrangement within this. And basically, to exploit the reaction conditions, you can either have a kinetic product or a thermodynamic product. Typically, POMs you get out are controlled by thermodynamics, which means your product is more stable than the reactant, and the kinetic product just means you have a smaller activation energy. But yeah, typically it's thermodynamic control. So next, why are we looking at POMs? Well, POMs have a ridiculously huge application. They're literally used in almost any area you can think of. So one interesting one is, I find it really interesting at least, that you can use them for anti-tumor activity. So you can use them in medicine, but you can use them for energy materials, you can use them for catalysis, you can use them to grow nanoparticles, artificial photosynthesis. It's really kind of limitless, it seems almost. And this is due to the unique redox capabilities. So as I mentioned earlier, because the structures are so stable, you can pump them full of electrons and remove them again to absolutely no damage to the particle. So you can kind of do loads of stuff with them. You can also take out these little edges of octahedra. So you could take out a metal oxide and plug in transition metals or tiny little molecules, which again adds to different properties, different uses, might make them photoactive, might make them magnetic. And yeah, they have really high thermal stability, soluble in a range of solvents, which obviously, as I'm a chemist, that's really important. And yeah, they're basically just kind of useful for everything, everywhere. So what I'm obviously looking at is the energy material side of things. A lot of research putting POMs into different layers is focused on dye-sensitized solar cells. Obviously, this is kind of a bit of an older, more established area than perovskites or PSCs. So in dye-sensitized, what I found was people kind of have put them in every single layer of the dye cell. So a dye cell is basically a mini solar panel. It's like a lab scale solar panel we can test on. And this in the middle is the structure of a perovskite solar cell, but to be honest, dye cells are kind of similar. Instead of this organic perovskite layer, you'd have your dye as the absorber layer, and then an electrolyte as well to facilitate charge transport. But basically what I found is in dye cells, they've been put in the encapsulation layer, they've been put in the cathode, they've been put in the semiconductor layers, the electrolytes, the bond-DP hybrids are the absorber layer, and then have been used in the photoanode. So they've basically been exploited for every part of this, and generally show a trend of increasing stability, facilitating charge transport, generally increasing photocurrent, that kind of stuff. So obviously they look quite promising. So we were kind of thinking, well, why have people not really used them perovskites? Because perovskites, even though they're well established and they have really high efficiency, stuff like that, their stability is still a bit poor. They still suffer from voltage losses. And as you can see, POMs generally have only been looked in perovskites for the electron transport layer. And even then, they've only been used as kind of a dopant, so kind of sprinkled on. And I don't think their full chemistry has been like realized or exploited. So that brings us on to what I have been looking at a bit more. The questions we were kind of wanting to answer was, can they be used to modify different surfaces or interfaces? So can you go between these layers? Can you use them in new areas? Can you use them in the absorber? Can you use them basically anywhere within the cell? And to make them kind of compatible with what we're doing, you have to have a low temperature for annealing, because a lot of the stuff you use in the solar cell to start with is going to degrade on high temperatures. So you don't want it to degrade with high temperatures. And then the structures are extremely tunable. Again, obviously this is an advantage, because if one doesn't work, we can probably just change it up a bit and try it again. Conductive with a star, I will explore that a bit more later. And then they're heat stable, water stable, generally air stable, depending what POM you use. So obviously you need something stable, otherwise as soon as you get outside, put it on your roof, it's just going to absolutely dissolve and be useless. There's also a question, more of a fundamental level, could they provide a charging or electron reservoir effect? So a lot of perovskites suffer from hysteresis, which is kind of a change in the current voltage curves in the forward and reverse regions. And could POMs, because they can store electrons, act as a reservoir and reduces hysteresis, or could they kind of store them up and inject electrons a bit later on, so you wouldn't get the voltage losses as much? We're not sure. This could be interesting. And also, could they be open to apply outside of the perovskite solar cell? Maybe we could use them with perovskite absorbers, but in a lot of different areas too, in terms of energy storage. So yeah, there's kind of a lot to look at here. The main kind of way I've started this off is to look at conductivity, because obviously if you can't transfer or carry electrons, then what good is putting this into an electronic device? It literally wouldn't make any sense. So had to have a look at the conductivity of these, benchmark them, and test out whether they'd actually be compatible with the devices. And also whether they can be used to tune the properties of all the conductive layers. So as we saw before, the whole transport layer, electron transport layer, can it kind of tune those levels to make them work a bit better? So my research is centered on the substituted kegging structures. By that, I mean, I've taken off a tungsten oxide and put in a lead, a bismuth, and an antimony. These were kind of chosen because you could source these from waste products in theory, and these are used generally in perovskite solar cells anyway, so it kind of seems fitting that they might work. So to go into the experimental setup, now it started off very kind of school play toy level, but it worked. And basically what I did was laser scribed conductive glass, so I had ITO, deposited a layer of POM on that, attached silver paste to each side where the POM was scratched off, connected these with crocodile clips to a source meter and measured the current and the voltage. As you can see, I kind of got these wiggly lines, which was because the crocodile clips obviously don't make great contact. But what was really interesting here is we were kind of expecting the same behavior all the time, hadn't really thought too much about it, and you get a really low conductivity, so 6 times 10 to the minus 7 Siemens per meter. It's quite low. Sort of expecting it, but yeah. But what I did realise by accidentally breathing on the sample, and you can see I've got COVID safe crossed out, kind of defining the lab practices, but essential here, because basically I realised that when I breathed on the sample, the conductivity massively increased. So it seems like the conductivity was dependent on humidity. And this could be interesting for a lot of reasons. It could open up doors to sensing. It could open doors to using solar cells in different environments, etc., etc. So obviously these results don't look too great, and I stepped up the experimental setup a bit. So again, don't laugh too much, but this is a Tupperware box with a sample holder and a PCB inside, which used pins instead of crocodile clips. So it made a lot more contact. I just designed these on Inventor, and then it was hooked up to a nitrogen Schlenk line and a water bubbler. So obviously I could fine tune the humidity that I was putting in and measure the conductivity simultaneously. And the results I got from this were actually a lot more clear and interesting. This is logarithmic scale, so you can see that actually conductivity like massively increased as humidity did. the ITO control did throw things off a little bit, but I do think it's quite interesting that depending on the substituent, you get very different discrete values for conductivity. They don't really tend to overlap. They're really reproducible, and that the substituent actually has quite a large effect on how conductivity works. So, of course, this has opened up a load more questions. So basically, clearly, humidity influences the conductivity, but why does it? We don't know the mechanism it works by. It could be ionic migration, it could be electronic, it could be to do with the oxygens, it could be, a wealth of things. It could even be proton hopping or anything like that. So naturally, the first thing to explore would be, why is this actually happening? What is this dependence? There's also an idea that it could be due to proton coupled electron transfer, and also kind of why are there different dependencies? So why do some of the curves kind of go this shape and some curve inwards? What is this exponential kind of dependence going on, and why isn't it linear? And why do the different lacunary atoms give different conductivities? I mean, we know that having different substituents does influence where the HOMO and LUMO are, and where the energy levels of where you're putting your electron are, but we don't really know specifically why. So my future work is going to be mechanistic studies to answer everything above. Different humidity environments. So instead of using water, a non-protonated solvent, so we can rule out proton coupled electron transfer or any proton hopping as a method of conductivity, and just see generally how conductivity is affected by different environments. Also by comparing to different metal oxides or doping the metal oxides, because obviously we've seen these papers where they work well with them. So if I could characterize them together and see how that influences stuff, that would be really interesting. Also some charge transport studies, assessing diffusion in terms of what's, where are the electrons coming from, where are they going, that sort of stuff. Another interesting question is, are bands forming? So people in the past have said that POMs have semiconductor-like properties, and they form these bands that are kind of like a conduction band and valence band, and kind of like a HOMO and LUMO, so they're kind of in between. And I think it'd be interesting to find out whether there are bands forming or whether they're acting as discrete particles or molecules. And also using electrochemistry a lot to assess hydrogen bonding. And lastly, whether the counter ion influences any of this, because what I didn't explain was that the POM isn't the TBA part. So you have your POM, which is like an anion negatively charged species, and you have to have a counter ion to get this in solution. And so does the counter ion actually influence any of this, or is it just redundant? Does it just sit there? And yeah, while I'm here, I'll just mention a bit more of the stuff I've been doing with POMs, because as I said, they could be used anywhere and anything. So fabrication and characterization of carbon POM hybrids for their use as an alternative to gold contacts. In perovskites, we use gold contacts. Oh, I'm up for time. Basically, yeah, made some carbon hybrids, and they look promising as well. So I've just gone to my last slide. Thanks for listening. Does anyone have any questions?
Thank you very much, Abigail. That was great. If the chat hasn't got any questions, I only really have one. Really interesting listening to what you were talking about. I only really recognised perovskites from my geoscience undergrad. I was wondering if there was like a where you thought there was like a critical point where you would get this humidity high enough to get the better conductivity, but then it's going to degrade other parts of the solar panel, say, if you thought anything about that.
Yeah, so it's a good question, because obviously the perovskite itself is kind of hygroscopic. It absorbs water and gets damaged by that. But the main limit to kind of getting damaged by water is the HTM layer. So it's a spirometad. And I'm thinking if we're using POM instead of that, it might even be more robust against water, if anything, is kind of my thinking. So when I say they've got low conductivity, they're actually analogous to non-oxidized spiro, which is like kind of good, not amazing. So actually, even if it was just a little bit more humid, I think device performance would improve quite drastically. The way those curves kind of set off, I'd say maybe like 30 to 40% relative humidity is probably where it starts getting good.
I think the only other question we have is from Tamara, who is asking, what do you think, or to what extent could ponds be used in marine technology, considering the durability to seawater and weather conditions?
I mean, I don't know a lot about marine technology. It's an interesting question. I can imagine they would be. I mean, they're quite durable, depending what pond you use. I guess it wouldn't dissolve in the water or leach, and I guess if they remain conductive whilst being exposed to water, I mean, sure, why not?
And then I think last but not least, Chris has asked, has the sensitivity been trialled with any other contact, i.e. not ITO?
Not yet. It's very early, but I'm definitely going to be trying it on a few different things. If you've got any ideas of what to use, I would be interested to hear.